So if you would permit me to do a slightly different type of video this time around. I don't want to make a habit of these because otherwise every other day I'm just going to put some crazy rant out, but I want to go rant mode for a little bit. I want to kind of complain or rant about not really open source stuff, which kind of drives me nuts when I'm trying to do these videos. Now, let me preface this by saying I'm not going to be calling anybody out with these videos. This is more of an educational thing so that everybody knows kind of what's expected of them in the community and why we're so adamant about it, as well as having some resources to go to see if they can be compliant. But even between the time that I started putting this video together and got it finished, some of the manufacturers that I kind of offhandedly refer to got their design files up on the board and they're uploading stuff every day. Believe me, I know. I have all of their GitHubs and their websites bookmarked and I look for this stuff. And in recent days, companies like Creality and Big Tree Tech have been making a real effort to do this. And actually some of the boards that I use for pictures in this video, just because I needed something to take pictures of that was on my desk, their files got recorded between the time I started this video and now, and actually cleared up some of the mystery about some things that I'll mention later on this video, which I was right about, which is relieving because I don't want to look any more stupid in public than I actually am. So I don't want to discourage that. I just want to encourage the behavior and maybe give some more resources and insight. That being said, here we go. Now, we know that part of the problem with open standards is the, well, lack of standardization. It's a communal sort of agreement, so there are, fortunately, sometimes organizations that pop up and try to put all of this into some kind of like organized codification. One of those being the Open Source Hardware Association, and you can go to their website, right there's the URL, and check these out, but I want to hit on like the first 6 of their tenets that they put down for open source hardware. And number 1, the prime directive is documentation. Hardware must have documentation, including design files. As a lot of you know from the last couple videos that I put out, I'm about to start another series, and the center point of that series is going to be the Ender 3 printer. Now, what brought me to this was, in preparation for the series, I'm going through a bunch of various new printer boards and hardware and things like that, trying to sort through like what I'm going to use for this series, what I'm not. But as you've noticed, I really only like to talk about equipment that is open source or making an effort to be open source, or, you know, I'm fine with commercial and closed source as long as that's what they are and they make no bones about it. The confusion about opening source, what source you have to open, when, and to what degree is a little bit muddled. So refer to item 2, the scope of the project, where the documentation must specify which portions are open design and which are not. It's fine to have some closed source stuff as long as you state that, but also refer to item A, the hardware must have documentation including design files. That's the fundamental. If you don't provide at least the complete base information, it's essentially going to be worthless. And you can't claim it's open source. I'm talking specifically about the hardware schematics. All of the grunt of the electrical stuff, all the indications of how everything's working, that comes down to the actual schematic. Just saying it's open source doesn't mean it is. Prime directive, provide documentation. And I know these places do this so that they can protect their market, but that's A, not the spirit of open source, and B, if somebody wants to steal your design and they do that for a living and they're going to produce a product, if they have a group of people dedicated to doing that from the time they punch in to the time they punch out of their jobs, it's going to happen pretty quick. So the only thing you're doing is inconveniencing the open source community, making them angry and making reviewers like me very uncomfortable talking about the boards because it's not compliant, A, and B, it's really tough or impossible to answer questions and troubleshoot particular issues if you don't know what the particular circuit is. I mean, it's great that you can say, hey, our board is 10 times better than the old ramp sandwich setup. It doesn't matter if we don't have the documentation and we don't know how to use it or what it's capable of. The problem is, with the explosion of all these new 32-bit boards, we have to kind of sort out, like, what are the ones that are going to be good and the communities are going to, like, catch on to and like, and which are the ones that are just going to kind of fall by the wayside. And that could happen either by, like, people getting the boards and saying, like, oh, I like this, or I don't like this, or it just doesn't work, or it doesn't have features that I want. Or that can happen with, hey, this board is supported and out there, so it's caught on with everybody, and therefore it's become very popular on all the forums where the smart people go and talk about how to solve your issues and what you can plug in and out and things like that. A great example of that would be like the ramps board. We've had like the schematics and the pinout diagrams and all that stuff like forever and ever. And that was a flawed board kind of from the start, but it became very popular because it was cheap and we had all the source available. So there were all kinds of workarounds that developed in the community and things like that. These in turn got rolled into the discussions on like, Reddit and the RepRap forums and YouTube and Thingiverse and Facebook and Twitter and all over the place. That all would have been impossible without the diagrams and the schematics and all that type of thing. The ramps probably would have still been very popular, but it would not have been the overwhelming go-to board for everyone. So think about that, and please, for the sake of the community, your effort in troubleshooting, being compliant with open source, and having tech nerds like me be able to talk about your boards in depth, please release the schematics. Let me give you an example in case you need an object lesson. I'll illustrate some issues with these boards that have come up and then play some hypothetical games and show you how they could be fixed if we had this information and we were sure about it. So here we go. Let's travel to a far-off fantasy land, a hypothetical planet that we will just call Earth. Let's say that on this planet, somebody created some 3D printing boards that use STM32-bit processors. And let's also hypothetically say that those boards are having problems with USB connectivity. Now, let's walk through the first steps of troubleshooting if we're talking about open source land. Pretty simple. Bring up the schematic files, see what the designs are, see where the pins are routed, and if that's all happy, compare it to the actual board hardware, and just check first for like no-brainer problems. For example, if you have this schematic, you can look up here and see, hey, WT actual F is going on here. 10K pull-up? Are you serious? With 3.3 volts? Diagnosis? It's a design issue. Whoever made this board didn't read the datasheet all the way through. Okay, so let's say that 10K resistor is actually a 1.5K resistor like it's supposed to be. Now we just go to the board and look and say, hey, wait a minute, that's not 1.5K. Problem solved. And the whole thing took like 2 minutes. Boom, there's your answer. No problem. Now, let's say we don't have those source files that we need. What are we going to do then? And again, not naming and shaming anyone in particular. You out there know who you are, and you people who are making an effort, you know who you are as well. This is just to show how much more difficult this is if you don't have what you need. And you can A/B that against the previous section where it's, hey, look how easy this is when we have all the information and we can answer these questions very quickly for the community. Because that may be a hypothetical problem for some boards that are on the market right now, who, for the sake of not naming and shaming, we'll call John Doe. So our John Doe board doesn't have the electrical diagram, so we can't easily diagnose if it's the design problem or compare the diagram against the board and see if it was a manufacturing problem. So, oh boy, let's strap in because that's going to be a longer process. First step, go to the manufacturer of the microcontroller to see what we're dealing with, even though they want to make fun of your tiny module publicly. That'll at least give us an idea of which pin it is we're supposed to be looking at, not in terms of what pin the board actually chose, because we don't know that since we don't have the source, but in terms of what are available, and then you have to make inferences. So, based on the manufacturer data sheets, plus information that we've gleaned from people that have experience with similar types of chips in other boards, as well as looking into the work that's been done in the firmware source, Marlin, or whatever, and using process of elimination to see which pins it is not, we can kind of conclude, hey, we think it's probably USART1. Again, an educated guess, probably right, but we don't know what to do with that. So, let's bust out a microscope and look at what we're doing. First, we're going to count down to which pins are USART1 and then just mark them here so we know where we're looking. Do a little bit of very careful powered down and powered up probing and scribble some notes on our desk so at least we know what we're dealing with at the point of entry in the MCU. But again, no schematic and no connection diagram means that we have no freaking clue what's in between the MCU and the actual USB jack. And if these happen to be a four-sided board or have a ground plane or something like that, it's very difficult to trace that because we're not sure where the connections are. So let's try to get an idea about what's going on the other side. So do some power down and power up tests on the USB jack and then some preliminary tracing. We'll make some educated assumptions like we're going to have a 1.5K or thereabouts resistor somewhere on that line. But what I found, or the hypothetical me in this situation may have found or may not have found, is that the pull-up has a different value when the board is powered and unpowered, and that value is 1.5K when it exists. That tells hypothetical me that the resistor is tied to an active device, or there's an active device with that level of resistance that's switched in and out of the circuit. And that is controlled by either the firmware or the bootloader, or a secondary intermediate program between the bootloader and the firmware. We don't have the bootloader source, of course, so we can't really know that, unless we take the firmware off, use a logic probe, and see what the pins are doing. Even though that's item number 3, if we want to be able to call our hardware open source, we have to document the interfaces. So even if you say no, the bootloader is proprietary, and consequently, if you say the bootloader is proprietary, you have to have written it from scratch. If you base it on open source examples, you have to cite those examples as well and release your source. But even if the bootloader itself is proprietary, you have to document the interfaces so that the software can be written to actually use them as they're intended. But we don't know that, so let's just make some educated guesswork. It looks like we don't have a direct connection between our USB and our ports on our microprocessor. If we did, in its simplest form, this is what it would look like. You would have small series resistors just to limit current, and then you would have a pull-up resistor of 1.5K on the D plus line. So let me sketch out what I think I'm seeing here is some kind of active device like a MOSFET or a switching transistor, a JFET, something like that, that's switching in and out of 1.5K resistor in various states. Sometimes it's on and pulling up, and sometimes it's not. But this is all based on a chain of guesswork from this shady character. I mean, would you trust him? I wouldn't. Look at him. I mean, when's the last time he even washed his hair? Now, I think I'm right, but that could be my middle name, Alex I think I'm right Kenneth. Let's assume this shady character right here is correct. That means the USB problem is software issue related to an active switch for the pull-up resistor, which probably has its gate triggered from a GPIO pin, because that would make sense. And since we don't have the source for the bootloader and we don't know if there's an intermediate program, we'll have to go fishing around in the firmware just to see if that even exists, and also in the back library, the support libraries for the STM chips. But let's go ahead and look at some more questions we might have if we don't have a schematic reference, and these are just basic functionality of board and things like that. Now, these STM32 chips have an advantage that some of the other chips from different manufacturers don't, in that they're 5-volt tolerant on a lot of the pins, but some of them are not. So it's possible that there are just level shifters on all of the ins and outs. Those are questions, basic questions we would need answered if we were to just even know what it is we're allowed to plug into the board and out of the board, what kind of signal levels we're going to be getting. Because it's a compatibility issue, and it could be a matter as simple as like, oh, that thing's not going to work with those signals, or it could be as dangerous as like, no, you're going to blow up that thing, or you're going to blow up your microprocessor. But it doesn't have to be that esoteric. It could be just as simple as jumpers, because as soon as the hypothetical me would put out a review with one of these boards, the first question is going to be, bruh, how do I set these microstep jumpers? To which my initial answer would have to be, bruh, I have no freaking idea. Maybe I'll have to blow up some step sticks just to figure out how these things are wired. Because we don't have a schematic. Now, not even mentioning it indicates to me that you're just saying, oh, we're defaulting to the standard. Well, we don't really have a standard for that. You could say the standard is the ramps board. I guess that's the closest we have to a standardization for those jumpers. So do we just assume that MS1 has a pull down resistor of a value of 100K? I mean, I see a 10K resistor right here, so vaguely near the jumpers. But that's just another thing that we would have to take a ton of time to figure out, or at least some time, as opposed to just looking at a pretty picture of a schematic and figuring it out from there. Now, okay, we're on like our third degree of digression away from the subject matter at hand, so I'm going to go ahead and end this segment. Sorry about the rant and the ugly drawings, but I just kind of wanted to get a point across. If you have any questions, let me know in the comments. All you manufacturers open there that are promoting these or creating and then claiming these boards are open source, please release schematics for us. That's part of the open source. The electrical diagram schematics are absolutely necessary, even to get in on the base level and figure out what it is we can plug into this board and how to fix problems people are having. So that's my rant mode over. Thank you very much for watching. If you like this type of content and you want to support, I have support links down here below. Please, I don't usually do this, but subscribe to the channel, ring the bell, blah, blah, blah. Thank you very much for watching. See you again soon. And until I do, get out there and make something awesome.